All right, next we want to look at properties of binary relations. So now that we know what binary relations are, they have several different properties. So first of all, we will look at the reflexive property and then anti-reflexive property. So a binary relation R on a set A, and notice when we say it's on a set A, that means that all of the elements in the relation are going to come from A crossed with A. Okay, so ordered pairs where both the first and second item in the order pair are going to be from the set A. Okay. So that binary relation is reflexive if and only if for every x in the set A, x is related to x. Okay. So what does that mean? So for the relation to be reflexive, every element has to be related to itself. So every single x in the set has to be related to itself. Okay. So to show that R is not reflexive, think about if we needed to show that this wasn't true, we just need, if this is for all x, this is true. To show that that is false, I just need to show that there exists one x where this is false. Okay, so if I'm trying to show that something is not reflexive, we just need to find basically one counterexample. So one element that's not related to itself. All right, so let's look at some examples. So we have A being a set 1, 2, 3, 4, and we want to determine which of the following relations are reflexive. Okay, so let's look at the first one. A is related to B if A divides B. Okay, so is this reflexive? Is it true that for every element in the set 1, 2, 3, and 4 that A would be related to itself? Okay, so that's, is A related to A, okay, for all A. Okay, so is 1 related to itself? So does 1 divide 1? Yes. Does 2 divide 2? Yeah. In general, like for no matter what a number, every number divides itself, right? So this is true because for all A divides itself. Okay. This is always true. So it is reflexive. All right, let's look at the next one. A is related to B if the sum of A and B is less than or equal to 3. Okay, so is every A related to itself, or is every element in A related to itself? So is 1 related to itself? Well, is 1 plus 1 less than or equal to 3? Yes. Okay, so 1 is related to itself. How about 2? Is 2 plus 2 less than or equal to 3? No. So 2 plus 2 is not less than or equal to 3, right? So 2 is not related to 2. And I only need to find one counterexample, and that's enough for me to know that it's not true for every single one. Sure, it was true for 1, but it wasn't true for 2. I don't even have to check 3 and 4. As long as I find one place where it's not related, I know that it's not related for all of them. Okay, so let me write this one. This first one was reflexive. Okay, we found one counterexample. So this one is not reflexive. Okay, and then let's look at the next one. A is related to B if A is less than or equal to B. Okay, so we'd have to go through every element and see if it was related to itself. Is 1 less than or equal to 1? Yes. Is 2 less than or equal to 2? Yes. Because that equals there, it's always going to be true, right? So A is less than or equal to A, okay, is always true. We can't find a counterexample, because of that equal in there. Okay, and so this one is reflexive. Okay, so that's reflexive. And then we have a related idea, anti-reflexive. Okay, so a binary relation on a set is anti-reflexive if and only if for every element x in the domain it is not true that x is related to itself. Okay, so that means that there does not exist a single x that is related to itself. Okay, because it's always not related. All right, so that's the idea. So let's check this one. A is related to B if A is greater than B. So let's see, could we ever find even a single x where A could be related to itself? Okay, well, if I look at A greater than A, this is always false. There's no time, no matter what A we pick, where A could ever be greater than itself. Okay, this is always false. Okay, and so for every x, it's false. Okay, so this one is anti-reflexive. Okay, let's look at the next one. A is related to B if the absolute value of the difference of A and B is greater than or equal to 0. Okay, so if I want to see if a arbitrary A is related to itself, I would go and check to see if A, okay, well, A minus A is always 0, the absolute value of 0 greater than 0, that's always false. Okay, and so this one also is anti-reflexive. You can't find a single A that would be related to itself. Okay. Okay, so one thing to note is that if a relation is reflexive, that means, okay, that every A is related to itself, then it certainly can't be anti-reflexive. Okay, so if every A is related to itself, that means every A is true. We certainly can't find every A as being false. Also, if we knew that it was anti-reflexive, there's no possible way it could be reflexive. So if we knew that it was always false, it certainly can't be that it's always true. Okay, so these things cannot be true at the same time, where it's both reflexive and anti-reflexive. But it could be neither. Okay, so if we ever have the case where sometimes A is related to A and sometimes it's not. So, for example, in our previous, like let's say, you know, we had this example in our last set of notes where we had 1 is related to itself and 2 is related to itself, but 3 isn't related to itself. Okay, well, it's not reflexive because, well, I can find a counter example right here where 3 is not related to 3. So this one is not reflexive. Well, does that mean that it's anti-reflexive? Well, no. To be anti-reflexive, we can't have any of the pairs being related to himself. But we do. We have 1 is related to 1 and 2 is related to 2. So it's not anti-reflexive either. So it can be neither. It just can't be both at the same time. Okay. All right, so that is reflexive and anti-reflexive. Let's look at some examples. So we know from the previous section that there are 3 different ways to represent a relation using ordered pairs, using a digraph, or using a matrix. And let's say we were given various representations and we wanted to ask ourselves, well, is this reflexive or is this anti-reflexive? How could I quickly look at the representation and determine whether something was reflexive or anti-reflexive? So let's start with the ordered pairs. Okay. So for being reflexive, I know that I have to have an ordered pair in which both the first and the second element are the same. Okay, so I could go through and just check. Do I have 1 is related to 1, 2 is related to 2, 3? So I could just, okay, in none of these do I have an ordered pair where both the first and the second elements are the same. Okay. And so, is this one reflexive? Well, no, I never have that 1 is related to 1. I never have that 2 is related to 2. I never have 3 is related to 3. Okay. Whereas if I look at the second one, I've got 1 is related to 1. I've got 2 is related to 2. I've got 3 is related to 3. And I've got 4 is related to 4. Okay. So hopefully you can see then that that's what I would want to ask myself here. I would ask, is the pair AA listed for all A in the domain? So in this first case, that's the question I would ask myself. And then if yes, then it's reflexive, sorry. If no, then it's not reflective. Okay, so here I don't have the ordered pairs. This is not reflexive. Here I do have, okay, 1, 2, 3, 4. All of them are there, so this one is reflexive. And I should be able to quickly check. Okay, I've got 1, 1. I've got 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, and 7, 7. Okay, the set, okay, is 1 through 7 for this one. There's no other elements. So this one is reflexive. Okay, this one has 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Okay, that's only has the numbers 1 through 6 on this one. This one is also reflexive. Okay. And then if I wanted to check for anti-reflexive, well, anti-reflexive is that I never have 1, 1, 2, 2, 3, 3, 4, 4. I never have a single pair. Okay, so I could ask myself, okay, is pair A never listed for any A? Okay. If it's never listed, then it is anti-reflexive. But if sometimes they are listed and sometimes they're not listed, then it would be not anti-reflexive. Okay, so this one I never get a single time where I don't have a 1, 1, I don't have a 2, 2, I don't have a 3, 3, I don't have a 4, 4. I never have a pair where both the first and the second are the same. And so this one would be anti-reflexive. Okay, and here, okay, because we had all the pairs, we know it can't be both reflexive and anti-reflexive, so all these are not anti-reflexive. Okay, I'm just going to abbreviate because I don't have a lot of room here. Okay. All right, so that's looking at the ordered pairs. All right, let's think about how that would look in a digraph. Okay, so in a digraph, if I'm looking to see if it's reflexive, I want to see if 1 is related to 1. Well, what would that look like in a digraph? Well, 1 being related to 1, I would see, like here, I would have to see a loop going from 1 to 1. Here, I can quickly see, oh, there's a loop going from 1 to 1. There's a loop going from 2 to 2, from 3 to 3, from 4 to 4. Okay, so if I would just, if I see a self loop on every single vertex there, then I know it's reflexive. Okay, so that's kind of the question I want to ask myself for the digraph. Okay, is there a self loop at every vertex? Okay, so if yes, then it's reflexive. Okay, then if it's no, not at every single one, then it's not reflexive. Okay, so here I can quickly see this is not reflexive. Okay, self loop, self loop, self loop, self loop. Okay, this one is quickly reflexive. Okay, 1, 2, 3, 4, 5, 6, 7. Every single one of them has a self loop. This one is reflexive. Okay, 1, 2, 3, 4, 5, 6. Every single one of them has a self loop. This one is reflexive. Okay, so I hope you can see it's much quicker for us to just visually inspect these and quickly determine that it's reflexive by just looking for the self loops. Okay, let's think about anti-reflexive. Now, anti-reflexive means there's never a pair that's related to itself. So are there 0 self loops? Okay, so are there no self loops? Okay, if yes, that's anti-reflexive. And if no, then it's not anti-reflexive. Okay, and so here I can quickly look, no self loops. Okay, so this one is anti-reflexive. Okay, this one that has self loops, clearly it's not anti-reflexive. Again, as soon as I see a self loop, I know it's not anti-reflexive. As soon as I see a self loop, it's not anti-reflexive. Okay, and then going back to this example like I pointed out before, if we looked at this one, when I say, okay, I don't have a self loop on every single one, this would be a good example of this is not reflexive because I don't have a self loop on every vertex. Is it anti-reflexive? Well, sometimes I have self loops and sometimes I don't. Okay, so it's also not anti-reflexive, and you can just really quickly look at that one and visually see that. All right, so that takes care of the digraph representation. Let's think about the matrix. All right, so for a matrix, if I want to see if an element is related to itself, well, let's just go up to this one first. This is like 1, 2, 3, 4, 1, 2, 3, 4. Well, 1 related to 1 is here, 2 related to 2 is here, 3 related to 3 is here, 4 related to 4 is here. Okay, what we can see is that those are all along the diagonal. So if I just look at the diagonal, that's all I need to consider. Okay, so if I were to see a 1 at every spot on the diagonal, that would mean 1 is related to 1, 2 is related to 2, 3 is related to 3, 4 is related to 4. If I see zeros at every spot on the diagonal, that means none of them are related. If I see 1 sometimes, zeros sometimes, it means sometimes elements are related to themselves and sometimes they're not. Okay, so in general, I can just ask, is the diagonal all ones? Okay, if so, then it's reflexive. Is the diagonal all zeros? If so, then it's anti-reflexive. Okay, so here you can quickly see that this one is not reflexive, but it is anti-reflexive. Okay, if I examine the diagonal here, it's all ones. This one is reflexive. Of course, it's not anti-reflexive. Okay, here this one's got a long diagonal, but I can quickly go down it. It's all ones. This one is reflexive. Okay, it's not anti-reflexive. Again, this one is a bigger one, but I just need to go down the diagonal. It's all ones, so it's reflexive. And it's not anti-reflexive. Okay. So in terms of which representation is most convenient, okay, clearly it's not the ordered pairs. You may think the matrix, you may think the digraph. I think there are contexts for each of them. I kind of like the matrix one. I feel like you can just quickly go down the diagonal and see that, but I think there's an argument that can be made for the digraph as well. But clearly these two representations seem to be much more convenient to quickly ascertain the reflexive, not reflexive property than trying to go through a list of ordered pairs. Okay. So that is our first couple relationships, the reflexive, anti-reflexive. The next one we want to look at is symmetric. So symmetric binary relations. A relation is symmetric if and only if for every single xy pair, x is related to y if and only if, this is the biconditional, so this is if and only if, biconditional, y is related to x. Okay. So, thinking about what we know about if and only if, what would have to be true for a relation to be symmetric? And this one's a little bit tricky because you might think that we always have to have the x is related to y and y is related to x. That's one option. Okay, so this would be, here we would have x was related, so x is related to y if and only if, so this would be true and this would be true. Okay, so we would have true, biconditional with true, okay, and that one would be, so this one is true. But there's another way to get the biconditional to be true, and that is to have false if and only if false. So as long as both sides of the biconditional have the same truth value, okay, this is also true. So the other way for it to be symmetric is that neither x is related to y nor y is related to x. They're both false. Okay. So basically it's if we have a pair that's related, then when you turn it around the other one's there as well. Okay. But if I don't have a relation, that's fine. Okay, as long as I don't have, x is related to y, but y isn't related to x. Okay, that would not make it symmetric. So I either have that they're both there or they're neither there. Okay. All right, so let's look at some examples. So let's say we've got a relation on the set of people in our class, and we have that x is related to y if x and y live together. Okay, and so if we take any two people in the class, suppose that x lives with y, okay, would it also be true that y lives with x? Well, yes. Okay, there's no way for, one person to live with another person, but that person doesn't live with them, right? So I'm either always going to have people that live together. So, like, I'm assuming that Nick and Patrick live together. I don't know that that's true, but I'm just assuming it is true. Okay, so if Nick lives with Patrick, then Patrick lives with Nick. It goes both ways. It's symmetric. Okay, whereas if I think about, let's say Josh and Jonathan. So if Josh doesn't live with Jonathan, Jonathan doesn't live with Josh. So it's either they're both true or they're both false. Okay, so this is an example of a symmetric relationship. Okay. The next one, x is related to y if x and y have the same parents. Okay. So if we went through the people in our class, not very many of them have the same parents. Okay. So it's mostly false and false. Okay. But we do have, once again, Nick and Patrick. Okay. They do have the same parents, and so, but if Nick has the same parents as Patrick, then Patrick has the same parents as Nick. Okay, so it's either both true or both false. This is also an example of a symmetric relationship. Okay. What about x is related to y if they have the same major? Okay. Well, I believe that every single person in our class is a computer science major, and so all we have is a bunch of true and trues. We don't have to have false and falses. Okay, we'd have just a bunch of, so every two people we picked, they would say, oh, I have a computer science major, and the other person, I do as well. Okay, so they have the same major, so this one is also symmetric. Alright, so just like there were reflexive and anti-reflexive relationships, we also have symmetric and anti-symmetric relationships. So let's look at anti-symmetric. So a relation is anti-symmetric if and only if for every x and y in A, as long as x and y aren't the same, then it's not true that both pairs are in the relation. So both x is related to y and y is related to x. Okay. All right, so what that means, okay, this is a little bit tricky, but there are a few different ways where we can get something to be anti-symmetric. Okay, so a relation is anti-symmetric as long as one of the following holds for every distinct. Okay, that means x and y have to be different for every distinct pair. Okay, so let's look at what this is. This is if, okay, x not equal to y. So if we had to write this out, we would think x not equal to y, then not x is related to y and y is related to x. So think about that, okay, as being, as being the, we need to determine the truth value of this. Okay, so as long as we have a distinct pair here, okay, we have true implies something for each one of these. Okay, if we're talking about a distinct pair, then x is not equal to y. Okay, so over here I have not and then something. Okay, so only true implies true is going to give us true, right? So what I need in here are all things that are false. And there's different ways to get this being false. Okay, so let's say x is related to y. So if I look at this, x is related to y, that one is true. But x is not related to, but y is not related to x. So this one would be false. Okay, so I'm just looking at the truth value of this right here. All right, so true and false is false. Not false is true. I get true implies true. This one will give me true. Okay. But that's not the only way to get it true. Okay, so if I have that x is not related to y, then this one would be false. But x is related to y, this one would be true. False and true is false, not false is true, true implies true is true. This one also gives true. And here, x is not related to y, so that one gives false. Y is not related to x, that one gives false. False and false is false, not false is true, so we have true implies true. This also gives true. Okay. So it's anti-symmetric, okay, if we either have x is related to y, but y isn't related to x. Okay. X isn't related to y, but y is related to x. And those are kind of the obvious ones. We have one of the pairs. The one that's less obvious and the one that can be a little bit tricky is that I have neither of the pairs. Okay. So x isn't related to y and y isn't related to x. Okay, this is the one that gets overlooked sometimes, and so just be careful. Okay, these are the ones that kind of are more intuitive. So it's anti-symmetric if I have one pair but not the other, or I have neither pair at all. Okay. And so we talked about reflexive and anti-reflexive. It's impossible for a relation to be both reflexive and anti-reflexive at the same time. This is not the case for be both symmetric and anti-symmetric at the same time, and it's because of this tricky one right here. Okay, so it could be symmetric if we always have false and false. Okay, so going back to if we have both of these, we have false if and only if false, that's true, and it'll be symmetric. Okay, if we have both of those, it will also be anti-symmetric. Okay, so it will be both symmetric and anti-symmetric when we have, these that neither pair ever exists. So it will be both symmetric and anti-symmetric. It'll make symmetric true for this one. It'll make anti-symmetric true right here. Okay, so let's look again at the same. Now normally, in a class, so if X and Y live together, I never have a case for, every person lives with themselves. So we don't, like with the symmetric and the anti-symmetric, that's why with the anti-symmetric we consider only X not being the same thing as Y. It should be two distinct things. So we're not considering that a person lives with itself. We're considering only distinct people. So if person X lives with person Y, then person Y lives with person X. That will be symmetric. That will always be true. We're never going to find a situation where we have X lives with Y, but Y doesn't live with X. And we're never going to find, a situation, but we can find a situation where X doesn't live with Y and Y doesn't live with X. So if it happened that it was always true that X and Y didn't live together, then we would have, so this one is definitely symmetric, as we saw in the last. So the question is it anti-symmetric? So I said before, I believe Nick and Patrick probably live together, and so this is not anti-symmetric. Because I do believe that Nick and Patrick live together. If they don't, they can inform us, and then we would have an anti-symmetric situation. Nick and Patrick seem to ruin all of our examples here. Not ruin, but you know what I'm saying. Like in the past class, I've had it so that there were no two people that had the same parents. And so this one was anti-symmetric. But Nick and Patrick have the same parents, so once again, while the other students in the class don't have the same parents, so they're not related, we do have that Nick and Patrick. So this one is not anti-symmetric. Because Nick and Patrick have the same parents. And what about have the same major? Well, in this situation, every single person has the same major. That's always true. We never have a false, so this one's also not anti-symmetric. We might want to add a new one, like X is related to Y if X and Y have the same T T number. I had to come up with an example where Nick and Patrick wouldn't have the same, okay, I think they have the same birthday, they have the same hair color, they have the same, okay, picture. So it's very hard, but I don't think they have the same T number. All right, so if we went through, all right, do they have the same T number? Well, there aren't any students in the entire class where they have the same T number. So this one would actually be anti-symmetric. Okay, so for any two distinct students, like we would have this, okay, X is not related to Y and Y is not related to X. We would kind of have this situation with the T numbers. They're always distinct, and so it would be anti-symmetric. All right. So just like we wanted to look at the graphs for, and see if we could quickly tell from the graph whether it was reflexive and anti-reflexive, we want to do the same thing for symmetric and anti-symmetric. Okay, so how can we look at the graph and tell if a relation is symmetric or anti-symmetric? All right, so let's look at the ordered pairs first. Okay, so with the ordered pairs, something will be symmetric if I have, like let's say I have A is related to B, then I also would have to have B is related to A. So I could just go through and check. All right, I have 1 is related to 2. Do I also have 2 is related to 1? No, I don't. Okay, so that one doesn't have its matching pair. Okay, so I can already tell that this is not symmetric because I would have to have for every single pair, if I have one, A is related to B, then B is related to A, and I don't have that here. Okay, so what I would have to ask myself is, for each AB, does BA exist? Okay, if yes, then it's symmetric. If no, then it's not symmetric. Okay, I already know there's a no here. Okay, so this one is not symmetric. Okay, if I go through this one, and of course we can just check you know, we can't, so 1 is related to 1, 1 is related to 1. Okay, so, but we can kind of take out the self-related ones. Okay, we really only need to look at the ones where they're distinct for symmetric. Okay, and so 1 is related to 3, 3 is related to 1. Okay, so I have both of those. And then I just look at any other pairs that I haven't considered yet. 2 is related to 4. Do I have 4 is related to 2? Yes. Okay. And so every single pair has its reverse pair in there. So this one, for each AB, does BA exist? Yes. So this one is symmetric. Okay. Again, I can disregard all of the 1, 1, the 2, 2, the 3, 3, the 4, 4, the 5, 5, the 6, 6, and the 7, 7. Okay. Okay, if it's there, great. If it's not, great. So either way, I have that either, okay, they both exist or neither exist. Okay, so 1, 1, does 2, 1 exist? Yes. 3, 4, does 4, 3 exist? Yes. 5, 6, does 6, 5 exist? Yes. 5, 7, does 7, 5 exist? Yes. 6, 7, does 7, 6 exist? Yes. Okay, every single one has its pair, so this one is symmetric. And the last one, again, let me take out 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. Okay, 1, 2. Does 2, 1 exist? No. Okay, So already I can see this one is not symmetric. Okay. How about anti-symmetric? Okay. So for anti-symmetric, okay, we could either have 1, 1. Okay, so we have to have AB, but not BA. Okay. So we essentially, let's just ask ourselves, is there at most okay, so we could have either AB or BA, okay, or neither of them, okay, but we can't have both of them as long as we don't have both of them. Okay, so here we would actually have to go and check. All right, I have 1, 2, but not 2, 1. I have 1, 3. Do I have 3, 1? No. I have 1, 4. Do I have 4, 1? No. I have 2, 3. Do I have 3, 2? No. I have 4, 3. Do I have 3, 4? No. Okay. So in each case, I had at most one of these. I never had both of them. So if I have all X's and no checks, okay, then I can see there's at most one of those. Okay, so this one is anti-symmetric. Okay. Okay, here it's symmetric. Okay, I only have pairs. I never, so when I have a 1, 3 and a 3, 1, definitely I don't have at most one. This one is not anti-symmetric. Okay. Here is not anti-symmetric. I have 1, 2, and 2, 1. This is not anti-symmetric. Okay, down here, let's check. I had 2, 3. Is there a 3, 2? No. 3, 4. Is there a 4, 3? No. 4, 5. Is there a 5, 4? No. 5, 6. Is there a 6, 5? No. 6, 1. Is there a 1, 6? No. Okay. So once again, we see, okay, we never have both of these present. As long as we don't have both of these present, it's anti-symmetric. Okay. All right. How about the digraphs? Okay, so the digraphs, if we think about, so for being symmetric, we would have to have that whenever A is related to B, B is related to A. Okay. Okay, so we would have to have an edge going both directions, okay, or neither direction. Okay, so never could we have just one arrow and not coming. So we either have both arrows or no arrows. Okay, so we could go through quickly, hopefully. Do we have both arrows? No. Okay, so we know that we don't have both arrows, so this one is not symmetric. Okay, do we have both arrows or no arrows? Okay, so if we look at like 1 and 2, no arrows. 1 and 3, both arrows. 1 and 4, no arrows. Okay, 2 and 3, no arrows. 2 and 4, both arrows. Okay, 3 and 4, no arrows. We've looked at every possible pair there. We always have either both arrows or no arrows. Does this always happen? Yes, so this is symmetric. Okay. Okay, so we have both arrows. We have both arrows. Okay. For 1 and all these other ones, there's no arrows. Okay. We have both arrows, both arrows, both arrows. There's never a time, okay, where we have an arrow that's just going one direction and not the other. It's either both or neither. So this is symmetric. Okay. Here, we've just got arrows that are going one direction and not both directions. So this one is not symmetric. All right. How would we know if it was anti-symmetric? Okay. So for anti-symmetric, okay, we could have at most one directed edge. So it could be from A to B, It could be from B to A, or we could have no edge at all. Okay, so one directed edge or zero directed edge, at most one directed edge. Okay, does this have at most one directed edge? Yes. Okay, so this one is antisymmetric. Okay, here I see all these double ones between, so this one's not antisymmetric. Okay, here I see all these doubles. This one's not antisymmetric. Okay, here they never double up. Okay, they're always one directional. So this one is antisymmetric. Okay. Once again, this one was probably a little bit quicker for us to go through than the ordered pairs. So the digraph is a very convenient representation. Okay, and let's finish up by looking at the matrix representations. Okay, so this one is a little bit trickier. Okay, so remember, we're only considering where x is not equal to y. Okay, so I'm just going to kind of take out the diagonal. I don't need to look at the diagonal. I'm only considering where x is not equal to y, so let me get rid of the diagonal. Okay. So let's start here. Like here, this would be like 2 is related to 1. Well, 1 is related to 2 is up here. Okay, so notice that. Let's say this one right here. This is 4 is related to 1. 1 is related to 4 is up here. So notice there's this symmetry over the diagonal. If I were to take this and fold it along the diagonal, each pair would fall on top of its, if this is AB, this is BA. If this is AB, this is BA. The one that it would fall on top of when I fold it over the diagonal. Okay, it's symmetric over that diagonal. So I would kind of compare these across the diagonal. Okay, what would it fall on if I folded it over its diagonal? And I would compare those ones. Okay, across the diagonal, the symmetric pairs. And I would check, okay, well, if it was symmetric, then I would have to have, okay, if AB, then BA. So these would have to be the same. They're either both ones or they're both zeros. Okay, so, okay, check if same across diagonal for symmetric. Okay, so if they're not the same, then this one is not symmetric. Okay, here zeros match up, ones match up, zeros, zeros, ones, zeros are always the same, so this one is symmetric. Are these ones the same? Okay, well, there's a whole bunch going on here, but let's just check the ones. Like I can see there's a bunch of zeros, and I know they're all the same, so just let's check the ones. So these ones are the same, these are the same, these are the same, these are the same, these are the same. Everything else is zero, so I know those are the same. All right, so they're always the same. Always either both zeros or both ones, so this one is symmetric. Again, this is a big one, okay, but we really just need to check across the diagonal. Here's a 1, okay, not the same over there, okay. So I see at least one that doesn't match. It's not always, so this one is not symmetric. Okay. And then if I wanted to check against for anti-symmetric, okay, so anti-symmetric, okay, you can have, like, you're tempted to say they're always different, like a 1 and a 0, okay, but remember it could be always 0, 0, so it's better to check that we never have 1, 1 across the diagonal. We can have 0, 1, 1, 0, 0, 0. 0, 0 is okay. Okay, they don't have to be different. It just can't be 1, 1. Okay. So anti-symmetric. Do we ever have 1, 1? No, 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 no. So this one is anti-symmetric. Do Do we ever have 1, 1 on this one? Yes, we do. So this one is not antisymmetric. Do we ever have 1, 1 here? Yep, we drew them all in. This one is not antisymmetric. Okay, here, okay, this one matches a 0. Okay, this one matches a 0. 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 Everything else is zeros. Okay, those are fine. It's just I can't have a 1 matching a 1. So if I just check the 1s, that should be enough. Okay, I always have a 1 with a 0, never a 1 with a 1. So this one is antisymmetric. Okay. So in this particular instance, I do believe that the digraph was probably the most convenient. The diagonals aren't too hard to check, but I feel like the graph is maybe just a little bit easier. Okay, we're at a good stopping place, and next time after Thanksgiving, we'll look at our last property, which is transitive, but we'll stop there for now.